Hello, welcome to the I believe it's fifth episode of the programming course. At the last session, we have written this code, which kind of explains and it doesn't actually explains. It prints all the odd and even numbers between 1 and 100, and that was it. We write the flowchart, the code, and everything. Today, let's begin with a for loop. And also, at the last session, we started to talk about loops. So let's start with another loop. We know that there are two types of loops actually. One of them is a while loop that we are familiar with, and the other kind of loop is a for. For kind of represents that either you can count the repeat times, or you know that there is an collection which you can iterate on them, and you kind of know how many items are present in that collection, so you kind of can count the repeat time that you're gonna need. So the for loop is handy when you kind of can guess how many times you're gonna repeat that instrument block. But the while loop is actually good for the situation that you do not know how many repeat cycles you're gonna need. You just know what is the condition for doing those condition over and over again. For example, in this situation, we kind of can know that the n is going to be between 1 and 100. We kind of can guess that it is going to be repeated 100 times. So we kind of can ditch the while loop and use for instead. So the syntax for the for loop is like for and some variable, for example our index, and the collection or the iteration that you're gonna pass. For example, I'm gonna say index is in a range of 100. That's it. And just print index. Yep, that's it. I'm going to comment the rest of the code so it won't be executed. So let's run this code, and what we'll see is that there is all the numbers from 1 up to excuse me, that's from 0 all the way to 99, and we don't have the 100. And if we needed the 100 itself, you could just say 101, so it would be from 0 all the way up to 100, as you can see. So what if we just wanted to start from 10 and go all the way to 100? Alright, the range could provide us that kind of thing. You can say for index in the range of 10 and 100. That's going to be the start point and the end point of the range. So let's see what happened. As you can see, the index has started from 10 and went all the way up to 99, not the 100. So if we wanted to 100, simply we could just make it 101 or 100 plus 1, whatever. It would be all the way up to 100. Actually, the range function accepts a third parameter. We call it step. As you can see, it's blue highlighted, and the parameter name is step. The step actually by default is 1, which shows we start from 10 and we go 1 unit at a time all the way up to 110. So we start with 10, we go for 11, then 12, then 13 and 14, and all the way up to 100. But if I change the step to 2, it would be 10 and then 12 and then 14 and then 16, 18, 20, all the way up to 100. Let's see. Come on. Yep, we start from 10 and we went straight to the 12, and we kind of skipped the 11 and skipped the 13 and went to 14, and then it's two step at a time for this range. So this could be handy if you wanted to just show the odd numbers or the even numbers, because we can see that the numbers are odd, even, odd, even, odd, even, and kind of this sequence is repeating until the end of the word, actually, because the set of numbers has no end point. All right, let's rewrite the late. Yep. Okay, let's rewrite this code using the for loop. It just says 1 is odd, 2 is even, all the way up to 100, which 100 is even. So we could just ditch the n and n plus 1, and we could write for n in range of 1 and 101. So that kind of produces the exact result regardless of the type of the loop we have used. We didn't use while in this code, but it just produced the exact end that we were looking for. So that was a bit easy, and let's go for another example, which we are trying to get a number. For example, whatever, let's call it just number. So, or no, whatever. We want to get this from user, so we use the input that we have learned from before, and I'm gonna say enter a number as a prompt, and I'm gonna directly cast this to an integer. So this would be an integer numbers, which is num, and I'm going to show numbers between 1 and number. So I can use just for I in range of 1 all the way up to number plus 1, because as you saw before, the range parameter stops at this number, and this exact number is not going to show up at this range. So I'm going to add 1 unit to it so that I could be the number itself. So I just going to simply print the I and see if my code is working or not. If I run that, it says enter number. I go with 6, and it says 1, 2, 3, 4, 5, 6. That's it. It's working like a charm. Now, let's find the dividers of the given number. Divider means that if you divide the given number to that number, it's going to have 0 remaining, and it means the number and the other number are dividable together. So let's begin. We know that the dividers of the 6, for example, in this in our last example 6, the dividers is going to be between 1 and 6, something among those numbers. And let's just divide the number to the I and check if the remaining is 0 or not. So if the remaining is 0, it's a divider probably. So I'm going to print this. I'm going to one block further to showing that this print is a sub instruct of the if block, and the if is a sub instruction of the for loop. Let's run this code and enter a number. I'm going with 6, and yeah, it has skipped the 4 and 5 because 4 and 5 are not in the dividers. Yeah, those are not a divider for 6 because you cannot divide 6 by them. And yeah, let's try another number. For example, 4, 1, 2, 4. All right, what about 10? 1, 2, 5, 10. That's working kind of great as expected. So you kind of can see the point that with that algorithm and some creativity, you can write the algorithm for a prime number or a perfect number. You kind of can write them both. So let's begin with the prime number. So what a prime number is actually, it means the number has no other divider except 1 and itself. For example, 5 is a prime number, which means it cannot be divided by any other number rather than 1 and 5 itself. So let's try to go for that. So in here I have I, which is in the range of 1 and the number itself. I just want to see if there is another number between 1 and the number itself, which the number is dividable by that or not. So at the first, I'm going to assume that the number is prime. So I assign true as prime, and I say, yeah, that number is prime. And I start from 2 because all the numbers, including the prime numbers, are divisible by 1. So I don't need to check this. So I start from 2 and the number itself, which if it is at the end of the range, it would be inside the range. So I remove that +1 part, and now the I is from 2 and a number before the exact number that we are looking for. So if number is divisible by any of those numbers, I'm going to override this prime and make it false. So the prime is actually false if the number is divisible to another number between 2 and number itself -1. So after doing that loop, I'm going to check if the prime is actually still true or not. If it was true, I'm going to say that the number is prime, and otherwise I'm going to say the number is complex or non-prime, whatever, or compound, whatever. I don't know the exact word. So let's begin. I'm going with 6. 6 is complex. What about 2? 2 is prime actually. Going well. What about 8? 8 is complex. 9. 9 is complex because it's divisible by 3. What about 7? 7 is prime. Nice. So that's kind of working, and I'm satisfied with the result. and I can just remove this part because the prime is now a boolean, which could be true or false. So the true kind of could be the condition if prime, which means if true or if false, because the prime could represent this condition is true or not because it's boolean itself. So I'm going to comment this part and make a copy of this to kind of show the perfect number or not. Let's just remove them. So let's dive into the definition of the perfect number. As you might not know, some numbers could be perfect, which means if you sum up the dividers except the number itself, it would be the number itself. So let's go for 5. The dividers of 5 are just 1 and 5 because 5 is a prime number. And what about the 4? 4, actually let's write above the 5 so it could be a bit ordinal. The dividers of 4 are 1, 2 and 4, just 3 numbers. And forget about the number itself, so let's get rid of the 4 itself and 5 itself. If you sum up these, you end up with 3, which is not 4, so the 4 is not perfect. And this other series going to add up to 1, which is not 5, so 5 is not perfect. What about 6? 1, 2, 3, 6, right? Yeah. Then let's get rid of the number itself, add up them, and boom, that's 6. So if you add up the dividers of the 6, it would be 6, which makes a number be perfect. So 6 is a perfect number. So what about 7? 1, not 2, only 7, because 7 is prime, and 1 is not equal to 7. What about 8? It would be 1, 2, 4, and 8, which if we get rid of 8, we end up with 7. Still not perfect. So let's write the algorithm. So I'm going to assume something called sum with the initial value of 0, and I'm going to repeat that for loop over there to just kind of see the dividers. And if we found the divider, we just kind of add this divider with sum, so it could be sum is equal to sum plus I, and you could just simply abbreviate. You could just simply write this as sum is plus equal to I, which are the same. This is just an abbreviation for that. I'm just going to use the expanded version for a better view. So after summing up the dividers, I'm going to check if this sum or this summation, whatever, is equal to number or not. If it was equal, so the number is perfecto, but otherwise not perfect. There is no other concept for not perfect. You just have to say not perfect. Sorry. So what about 5? 5 is not perfect. What about 6? 6 is not perfect? Interesting. So 6 is not perfect. How come? Oh, we have to include 1. We have to start from 1. Yeah. Now 6 is perfect, and the 5 is not perfect, 1 is not perfect, 2 is not perfect, 7 is not perfect, 8 is not perfect, only 6. But there is not only 6, there is another number. I mean, there are a lot of numbers which are perfect, but after 6, I believe it's 120. No, 120. 6. I kind of forgot that. Let's find out. I'm going to let's check all the numbers from 1 all the way up to 1000 and see which are perfect. So I'm going to ditch this input. I'm going to just comment it, and for number in range of 1 and 1000, I'm going to check this, and only if it was true, I mean if it was perfect, I'm going to say that num is perfect, whatever number it is. I'm going to run this. 628 496. Those are really separated. So if we go up to 10,000, it would be, no, it's still calculating. Interesting. That was a bit hangy. Only 4 numbers are perfect at the range of 10,000. So, not all of the numbers are perfect, and kind of not all of the humans. So that's an algorithm for a perfect number, and a bit examples about loops and how they are working, how they can help you, and more importantly, how they can be a part of themselves. In this for loop, we have another for loop. We could just have another for loop inside this for loop. What about while, you ask? You kinda can have while inside for and for inside while. It doesn't matter as long as they are finite. It doesn't matter, because if it is not finite, you kind of you're going to ruin the definition of the algorithm. The algorithm must have an ending point. For example, if I write while true has no ending. So while true with an empty body, which we call it pass, never finishes. It never reaches the point to starting to find any perfect numbers. By Control C, I can break it, and by breaking it, it just stops working and goes out. It is actually a keyboard interrupt, which you can interrupt the script using keyboard, but there is no input because of this while true, because while true has no ending, and we cannot go any further step in the script. So this program is kind of faulty. And if I remove this waiting loop and rewrite the code, it takes a minute, not a minute, I mean it takes some seconds, and it gets me the result. So what about 100,000? It's taking to know what? Not any perfect number in range of 100,000? What about 10 million? You kind of can write the algorithm and tell me, is there any other number in range of 10 million? If it was, just tell me in the comments. And thanks for your time. I hope you enjoyed it. If you did, please consider sharing this with your friends. See you.